for everyone to come back there to listen to the second part. I would just like to start with a quick summary from yesterday to refresh everyone's memory. Just the key points that I talked about is that upwelling deep ocean waters in the Southern Ocean really sustain a large part of the ocean anthropogenic carbon sink in the global ocean. That most carbon in the Southern Ocean is stored in moat and intermediate water masses that go below the subtropical gyre. That observing the ocean carbon sink is awfully difficult, and even more so in the Southern Ocean because of the scarce observations that we have there. That large efforts are made at the moment to improve the observation coverage with sailboats, sail drones, and Argo floats. That simulating the Southern Ocean natural carbon cycle is also difficult due to model drifts and the model setup, and that makes it hard to quantify or simulate the total carbon flux in the Southern Ocean. And then there's much better agreement between models with respect to the Southern Ocean anthropogenic carbon sink than the natural pre-industrial carbon sink, because the anthropogenic carbon sink is mainly due to physical changes or physical circulation, and the natural carbon cycle is largely affected by biology and different other things. So going on from there, I realized yesterday when I gave the presentation that I should have probably introduced a little more the basics of carbon uptake in the ocean in general, because you're not all working on the carbon cycle on biogeochemistry. So I wanted to do this just a bit here in a small sketch. So the flux of carbon between the ocean and the atmosphere in general is proportional to the partial pressure of CO2 in the atmosphere and in the ocean. And if there's more CO2 in the ocean that goes into or the partial pressure of CO2 is higher in the ocean, then it's outgassed into the atmosphere and vice versa. And the flux is then driven also proportional, but the proportional factor depends on winds and other quantities. And if carbon in the ocean would just be as there's CO2, that would be the end of the story. But it is not. The CO2 reacts in the ocean with the water to create carbonic acid, and that then falls into hydrogen ions and bicarbonate ions. And the hydrogen ions that are freed, they react again with carbonate ions to create even more bicarbonate ions. So the carbon that goes into the ocean doesn't stay there as CO2. It's transferred into different compartments of the carbon system. And the total dissolved inorganic carbon in the ocean is the CO2, the bicarbonate ions, and the carbonate ions. So the more the ocean can transfer CO2 to these other compartments, the more CO2 can be taken up afterwards by the ocean, because once it's not anymore there's CO2, the partial pressure decreases, and the more CO2 can come back into the ocean from the atmosphere. So this cycle and the different equilibria between these equations are really crucial for the ocean carbon uptake. And it's especially the carbonate ions here that the more carbonate ions there are at the surface ocean, the more CO2 is transferred to bicarbonate ions, and the more CO2 can be taken up from the atmosphere. So this is basically the very simple biogeochemistry or carbonate chemistry that is behind the whole uptake and the difference in uptake at the ocean in different regions. And then if we just look at the carbonate ion concentration, we would expect that the uptake of carbon is highest in the tropical oceans and lowest in the polar oceans. But the uptake is not just, but then if you look at the storage where the anthropogenic carbon actually goes, we see it goes mostly into the North Atlantic and the Southern Ocean, as I said yesterday already. And this is because it's not only the atmospheric ocean equilibrium, but it's also, or mainly, how the ocean brings the carbon below the surface and replaces the surface water by older, deeper waters. So this was just a very brief excursion, more or less, into why the carbon cycle, or how the carbon uptake works and what is behind it. Something that I should probably have done yesterday, but better late than never, I guess. And these are the formation zone of North Atlantic deep water. That's why the storage of carbon is high here, and this is the formation of moderate and intermediate water in the Southern Ocean, where we see then this large bands of carbon storage there. And going on from here, I thought once we look already at a map of carbon storage in the ocean, of dissolved inorganic carbon storage, we can also see how these estimates, or how the carbon storage changes over time. So here you're seeing the uptake of carbon since pre-industrial time until 1994 at the top, and below you see the storage, the additional storage from 1994 to 2007. What we can also already see is that there are differences in there's a variability in the storage, that some regions tend to be more effective at some times than at others, if you compare it relatively. For example, here the South Atlantic is almost as strong as the North Atlantic, while it was different before. So there's a large variability on decadal timescales or longer timescales in the way the ocean stores the carbon. It's not always just the same way, because circulation changes and has its own variability. And if you look into more recent data, so these are estimates of the carbon storage for 2 decades, from 1994 to 2004, and from 2004 to 2014. We can see again that the Southern Ocean stands out as the region where most of the carbon is stored. But we can also see that from one decade to the other, there's a huge variability, whereas here in this decade there was large storage in the North Atlantic and less large storage in the South Atlantic, and the situation has kind of inversed from one decade to the other. But whatever time period we look at, it's always the place where the moderate and intermediate waters from the Southern Ocean go to that show the highest uptake. So the general pattern doesn't change that much, but we can still see some large variability, which is important if you want to understand changes on shorter term timescales in the ocean in general. So this was just to show that we can not only observe the carbon sink in the Southern Ocean and in the global ocean by using RC CO2 fluxes, but we can also use interior ocean observations and see how the storage of carbon changed, whether there's more carbon or less, by using observations from inside the ocean. And then we can also, so this is a quite messy plot, we can also look at how the models simulate the storage. So what you're looking at is, at the left side is the storage until 1994, and this is the estimate that you have just seen before. And this is another way to estimate the carbon storage. I'm sorry that I don't have the time to go into the details how these different observation-based estimates work. That's just a different way to estimate it. And this is then the estimate from 2000. Oh, it should be the other way around, from 1994 to 2007. And we see these different patterns that you saw before. It's basically the same data that is underlying these plots. And here you see how models perform for the same time scales. And we see that the models show the same patterns, with high storage in the North Atlantic, high storage in the Southern Ocean, and also show kind of increase in storage from here to here, or from here to here, but it's weaker than the observations. And then we see the differences. And so what we see is that models, if it's blue, it means models store less carbon than is estimated by observations. And it's a kind of reoccurring scheme, whatever timescale or whatever observation-based estimate we look at. So we see that models in general underestimate the carbon storage and the carbon uptake. But we also see that for almost the same time period, so pre-industrial until 1994 and pre-industrial until 2002, for this time scale, the models overestimate the storage in the really Southern Ocean, and for the other one, they underestimated. And this is not really due because of the 8 years of difference. This is due to the differences in these two observation-based estimates. Just to show that it's not only the models that differ, so it's hard to say the models underestimate the real storage, it's also the observation-based estimate that still have large uncertainties and that we don't really know which one of these is the best. So it's really hard to say which one, not only if the models agree with the observations, but if the observation-based estimates agree between each other. So again, the reoccurring scheme from yesterday, once we go to the Southern Ocean, it's hard to tell who's right and who's wrong. But the general idea is the same. So we know what's going on, but we need to do more effort to really quantify or get the numbers right. And just to show you this underestimation in a slightly different perspective. So here we have the anthropogenic carbon storage until 1994, and here from 1994 to 2007. And here the respective observation-based estimates of these two quantities. And then here we have the models, and we see that models who underestimate the storage until 1994 also underestimate the storage or the change between 1994 and 2007. But in general, all models underestimate the storage for both periods. So this too low in this perspective and too low here. But yeah, so we know that the models have some issues in that perspective, but we are working to figure out why. And a couple of things I've shown you yesterday already: the late starting date that influences the uptake of carbon, and other things I'm going to talk about now when I discuss the future ocean carbon sink in the Southern Ocean. So this would be really the second part of this talk, to talk about the future of the Southern Ocean carbon sink and how we think it's going to evolve, how certain we are about this, and what we can do to reduce uncertainties. And yeah, so we'll dive directly into this. So this is a plot you've seen yesterday, I think. If I remember, I gave another lecture yesterday as well, so I'm not sure if you saw this. So on the left side, there's the Southern Ocean anthropogenic carbon uptake for different CMIP6 models. So fully coupled Earth system models with a dynamic atmosphere, dynamic land vegetation, and a dynamic ocean. And we see that the Southern Ocean anthropogenic carbon uptake varies a lot over the 21st century, with some models simulating an uptake of 200 petagrams, or the highest model is around 305 to 310 petagrams. And what we also see is that the differences in the global estimates are very similar. So most of this uncertainty actually comes from the Southern Ocean. So it's really important to understand why this difference exists between these models and which one is right, if it's on the upper side, on the lower side, if it's somewhere here in the middle where a couple of models cluster. Then we can understand the Southern Ocean anthropogenic carbon uptake in the future better, and also the global anthropogenic carbon uptake. And just to show you this in a slightly different perspective on a map, where on the right side here, where we have the cumulative anthropogenic carbon uptake, and each grid cell for the model in mole per square meter, so the entire carbon that went into the ocean at this place from 1850 to 2100. We see the model at the lowest end here looks like this, so there's very weak uptake, and the model at the highest end from GFDL, which is here, has a very high uptake in a lot of these zones. And what we see as well is that a lot of this uptake happens along this white line here, which shows approximately the polar front, where a lot of the circumpolar deep water upwells, and then it moves northward to the subtropical frontier, where it gets subducted, or somewhere before it gets subducted into smooth and intermediate water, and leaves the surface ocean again. And it's in this zone really where the uptake happens, and then where the storage of the carbon happens. So this is a crucial zone for the uptake of anthropogenic carbon in the Southern Ocean, this interfrontal zone. And the question now is, can we reduce uncertainties of the future uptake in the Southern Ocean? And by reducing it, ideally, we also get a better understanding of the carbon uptake dynamics in the Southern Ocean. And the method that I've used to do this, and I'm going to present results from a paper that I published 3 years ago, is the method of emergent constraints. And this is actually, I don't know if some of you have worked with model weighting or something. This is not a way to say some models do better than others. This is a different perspective on the issue. It's saying all models are equally valid in simulating a mechanism in the ocean, but because they have different boundary conditions, they get to different results. So, for example, what could be a simple example, or what I'm going to show soon is that the denser the surface waters are in the Southern Ocean, the more deep water is created, and the more carbon is taken up by the Southern Ocean from the atmosphere. So the models, for a lot of different reasons, might have very different sea surface densities, but for a given density, each model would give us the same amount of mode in deep water formation and the same amount of carbon uptake. So we say we have an observable variable here on this x-axis, in this case, the Southern Ocean sea surface density, and we have a quantity that we want to constrain and that we want to know better. In this case, the uptake of anthropogenic carbon over the 21st century, and then we plot all the models on the scatter plot, and we see that for a given boundary condition, so for a given sea surface salinity, all of the models simulate a given carbon uptake, and they all lie on the same line. So if you moved one model, if you changed this boundary condition for one model, we would expect it to move along this line. And if such a relationship exists among models, then we would assume that if all the models have the same relationship, the same sensitivity of between an input and an output variable, we would expect the real world to be on this line as well. And then we can take the observations of the variable that is on the x-axis and go up here and say that this is probably the most likely value for the unobservable variable or the projection into the future. And this gives us then usually a smaller uncertainty around our estimate than just taking a multimodal average and the standard deviation, which would be much higher. And I'm going to show you in detail how that works in this case of the Southern Ocean. As I said, we have this important zone here between the subtropical and the polar front. And what you see here is the sea surface. It's not the sea surface density, it's the sea surface salinity. Because in cold waters, the differences in density are mainly to 95 to 90, even more percent driven by sea surface salinity. And temperature doesn't really affect density at this point anymore. So we don't even have to know the temperature, we can just go with the salinity. And we can see that here the salinity is higher in this region. This salinity in this region is really that is important for the deep and intermediate water formation. And if you look then in the models, a large quantity of models from CMIP5 and CMIP6, we get this nice relationship between the sea surface density or salinity. We can put in whatever variable you want here. It's going to be the same plot, and the volume of ventilated waters, which we calculated for each model. And you can see that the higher the sea surface density between the polar front and the subtropical front is, the higher is the volume of ventilated water in the interior ocean. So higher surface density, more water is getting into the Southern Ocean, into interior Southern Ocean. And we get this nice line. And we also put the observations on this plot. You can almost not see them. They're lying here because they actually fall ideally and perfectly on this line, which shows that, which suggests that this relationship is actually not only holding in models, but also in the real world. And just to show you how this looks like, where the waters go, it's very different in these models. So these different colors from here to here are the volume of ventilated waters where the sea surface waters go to, and we can see that some models have very deep ventilation of the Southern Ocean, whereas others, like this one here, has a rather weak ventilation. And here are the observations. So we see that a lot of models underestimate the sea surface density and the volume of ventilated waters, which suggests that they probably also underestimate the anthropogenic carbon uptake. And this is where I'm going to now. So you see here again the sea surface salinity for the observations from the World Ocean Atlas, for CSM2 for the model with the lowest uptake, here, and then for GFDL, the model with the highest uptake. And here are the numbers for the average interfrontal salinity in the zone. And here's the numbers for the integrated anthropogenic carbon uptake in the Southern Ocean. And what we can see here very, very nicely is that the model with the low uptake really has a very low sea surface salinity, and the model with the high uptake really has a very high sea surface salinity. And if we then look like how that looks like on a scatter plot, here on the left side, here we have the annual mean sea surface salinity between both fronts. We get this nice linear relationship and between this salinity and the cumulative anthropogenic carbon uptake. And so we are confident that this is really the mechanism that drives the differences in the model. Then we take the observations based on satellites of the sea surface salinity, and we go here and find that the cumulative uptake in 2100 is likely much higher than we would have expected based on most of the models, because they all appear to underestimate the sea surface salinity in that zone. And to show this in a probability density space, so if we assume before for all models a Gaussian distribution, we get a most likely uptake of around 245 petagram under large uncertainty. And after the constraint, which is basically an uncertainty range around this place here where the observations are, we get a much higher uptake, around 14 to 18% higher. But most importantly, it's much less uncertain, so around 50% less uncertain, being indicated here by the width of the probability distribution or by the height of it, which are both related, obviously, in a Gaussian distribution. And which is also important that this relationship doesn't only hold for CMAP6 models, it also holds for CMAP5 models. It also holds for different scenarios, so we believe that it's indeed a very stable relationship and that it explains really the differences and that we can use these observations to reduce the uncertainty. And we looked a little bit further and tried to understand what drives the differences in the mean surface salinity, but there's a lot of factors that play into it: evaporation, precipitation, upwelling of circumpolar deep waters, melting of sea ice, and or the wind strengths, the place of the Antarctic circumpolar current. But there's not one of these that explains this difference. So every model has a different way to finally come up with the sea surface salinity, or whatever sea surface salinity this model has allows us to determine the amount of anthropogenic carbon it will take up. So we can't explain what is behind the difference, or we can't find one factor that is behind the difference in the mean sea surface salinity. We can show that if we know that, we know, or we have a very good handle of how much carbon is going into the Southern Ocean in the future. And another way to corroborate our results, to be more confident about this, is to do the same thing for the carbon uptake until 2005, where we actually have estimates based on observations of the actual carbon uptake that this has happened. And you see the same plot now as before, that most models underestimate the sea surface salinity, so they also underestimate the uptake until 2005. You see the same constraint with a larger uptake after the constraint and reduced uncertainties. And here we plotted two data-based, observation-based estimates as well. And what we see is that the constraint actually moves the prior result or the unconstrained results closer to the observation-based results, getting them into better agreement, which again increases the confidence that this constraint really works, that this mechanism is valid, and that the Southern Ocean has taken up more carbon than we think based on these model simulations, and will continue to be a stronger carbon sink than we thought before, which is good news. If more carbon goes into the ocean, then our carbon budget that we can still emit to is likely a bit higher than previously estimated by these Earth system models. So for once, there's good news coming out of this work. And here we then remade also the time series, because this was only until 2005 or 2100, but we can actually calculate that for any year that we want to, and that's what we did here. And so I think in this time series the message comes across even more clearly, You see the unconstrained or just the multi-model mean with the standard deviation. Here is the lightly shaded, and then with the best estimate, the dashed line. And the constraint estimate is the solid line and the less weak shading or stronger shading. And there you can really see that the previous estimates just the multi-model means are much lower than the constraint estimates for both scenarios here that are shown. And that the uncertainties are really reduced, so we can give a much better estimate of what we think is going to happen in the Southern Ocean or the Southern Ocean carbon cycle. And what we then here you can see it just for 2100 as the range or the ±1 standard deviation, and can also see that for the lower emission scenarios, it even gets out of this range, just slightly out of the range after the constraint. So it's really a big difference that was made. Then there's just a table with all these numbers that you can, if you want to look them up or if you need them at one time. And there was a second study similar that was published a bit later that didn't look at the sea surface salinity or density as a proxy for the deep water formation, but directly looked at the stratification. So I just wanted to show this here to make the story complete. And I always have difficulties to understand the spaghetti plot here, so I will go slowly through it. So the colors show the cumulative uptake in the Southern Ocean, excluding the sea ice zone. That's why the numbers are a bit smaller, until 2100. So red means high uptake and blue means low uptake. And this mean density bias relative to the surface means the difference to the observed density gradient. So this is here, it means that there's a larger gradient in these models and a lower gradient in these models. And if the density gradient from the surface to 2000 meters is higher, that means that the ocean is more stratified and less well ventilatable, or the ventilation is probably more difficult. And if the lines are here, it means the ocean is less stratified and ventilation is easier. You can just by eye see that models with the highest uptake are less stratified and that it's easier to move water from the surface to the deep ocean, and that these models with a very low uptake have a very high stratification, a stronger gradient from the surface to the deep ocean, and hence ventilation in these models is probably much more difficult, which goes into the same, it's basically following the same ideas and coming to the same results and showing that interior physical observations or surface ocean observations lead to the same results, that the ocean will take up more carbon than we thought based on previous estimates. And to come back to the ocean biogeochemistry, so these were biases in physics, how they're going to influence the future uptake of carbon in the ocean and how we can reduce these uncertainties. Another point that differs across models and leads to differences in the future carbon uptake are biases in the ocean biogeochemistry. So this is a similar plot that I showed you before that I took from, sorry, I forgot to enter the references here, but I think it's from NOAA. And it's basically, it shows again that this carbonate ion here is crucial for the amount of CO2 that can be stored in other parts of the dissolved inorganic carbon and components. What we see is with increasing CO2, we reduce the pH, and then this equilibrium between carbonate ions, bicarbonate ions, and CO2 changes. So the more acidic the ocean becomes, the more carbonate ions here are consumed, and they're going to be less abundant in the ocean. And the more bicarbonate ions we get at the beginning, and if we go to very extreme pH values, they decrease again, because most of the carbon would then be available as CO2. And so it's highly important how much carbonate ions are in the ocean at the moment. And if models have a bias with respect to carbonate ions, they will have a bias with respect to the carbon uptake. And this can be quantified by the Revell factor. And the Revell factor is a quantification of how much carbon is going into the ocean for a given change in atmospheric CO2. So if the atmospheric CO2 increases by 1%, and the carbon in the ocean would also increase by 1%, that would give you a rel factor of 1. And to make it more complicated, it's the inverse, so it's the change in atmospheric CO2 divided by the change in ocean DIC. So the higher the rel factor is, the smaller is the anthropogenic carbon uptake for a given increase in the atmosphere of CO2, and the lower it is, the more the ocean can take up. And this is basically the picture of the carbonate ion concentration that I showed you before, just inverted. So just chemically, the tropical oceans can take up more anthropogenic carbon, and the polar oceans less, because they are colder, and the already colder waters can take up more CO2, so they've already consumed more of their carbonate ions there. And then if you look how models compare, how they simulate the Revel factor, they do a very good job in general. So the patterns are similar, with high Revel factors in the southern and Arctic Ocean, and lower Revel factors in the tropical oceans. And so they look very similar, but if you go into the details and the differences, you can really see that there's a difference in the polar oceans. In the Southern Ocean, the Revel factor seems to be too high in the Earth system models, and in the North Atlantic and the North Pacific as well. And although these are quite small differences, they still affect the carbon uptake. So as the Revel factor is too high, the models underestimate the uptake of anthropogenic carbon. So there should be an additional correction for the carbon sink in the Southern Ocean based on this too high Revel factor. We found this after we published our results, so it's not in that paper, but we used it for correction of the global anthropogenic carbon sink in another paper from 2022. So we have to, if we look at projections to reduce uncertainties, we have to see how these models simulate the overturning and the deep water formation, more intermediate water formation. And we also have to look at how well they simulate the carbonate chemistry at the surface ocean, because that also impacts the uptake of carbon. So it's a complex interdisciplinary subject to look at the carbon sink, and especially in the Southern Ocean, it's complicated but interesting. If it's not complicated, it's not interesting actually. And now I just wanted to show you results from a very recent publication from 1 week ago. So I didn't really have the time to read this in detail, but I still wanted to bring it up because it shows some nice also spatial differences. So here, Precious Monge and co-authors looked at different regions of the Southern Ocean. So you have the subtropical region, you have the subantarctic regions, and the Antarctic region. So we basically go from the northern Southern Ocean to the southern Ocean. And we have here the estimate for by Earth system models in blue and orange, and then the estimates from the PCO2 products for this period. And we can see that for the present date time, so which is in blue, that most of the uptake actually happens in the subtropical region, so it's 47%. And in the subantarctic and Antarctic regions, it's around 1/4 in each of these regions. But then when we go to the future, the uptake increases in all of these regions. But the subtropical regions, where most of the uptake happens at the moment, will only be responsible for 1/4 of the uptake. And now at the end, half of the uptake is going to happen in the Antarctic region. And the reason for these are complex. And as I said, I didn't have time to read and understand everything, but a large part of this difference of the moving of the uptake from the northern Southern Ocean to the southern Ocean is linked to the change in the sea ice fraction. So here you have time evolvement from left to right, so from today to 2100, and from the upper end of the plot to the lower end, you have the latitude. So this is the northern Southern Ocean integrated to over the longitudes to the southern Ocean. And in color, you have the uptake of carbon from the atmosphere. We see that at the moment we have large uptake here and less uptake in these zones. But if we go into the future, it all increases, but most of the increase really happens here. And a large part of this increase is associated to the loss of sea ice fraction, which you see here. So you see how much the sea ice is changing, and here there's really a huge loss of sea ice that coincidences with the amount of carbon that is taken up by the ocean in this region. So all the water that upwelled before below the sea ice and was transported to the deeper ocean as bottom water now comes up where there's less sea ice, so it can take up more carbon from the atmosphere and then take that with it to the deeper ocean. So there's a huge shift. Although the Southern Ocean remains a carbon sink, there's a huge shift of where the carbon is going to be taken up due to climate change, which I think is also very interesting and helps us to understand how the fluxes change in the future. Yeah, so these were all these results that I showed you were from typical CMIP simulations following SSP scenarios. But in these scenarios, we don't really know how the ocean carbon sink would look like in a 1.5 degree world or 2 degree world or 3 degree world, because for each of these scenarios, these models simulate very different warming rates, and usually until 2100, the temperature is not stabilized, so we don't know what happens if temperatures stabilize and if atmospheric CO2 decreases again with the carbon sink. And I just want to show you some results of different kind of simulations that we made. The algorithm to make these simulations were developed here in Bern by myself and colleagues, and then Jonas Silvi, who's working as a postdoc, did a model intercomparison project where more than 10 different Earth system models around the world ran these simulations. And the thing of these simulations is they don't follow any more given socioeconomic pathway prescribed by CMIP simulations or the IPCC. Now we made simulations that allow all models to converge to the same global temperature, to the same global warming. So in this case, 1.5 degrees. And then they all have very different emissions to go there. So these are the CO2 emissions in each model. So some can remain high to get the same warming, others have to reduce emissions very strongly. And they all converge to the same warming, and they all, at the end, converge closely to zero emissions to stabilize temperatures. And the anthropogenic CO2 is very different than in these simulations. And this allows us then to look, how's the ocean carbon sink going to look like once temperature stabilized, once atmospheric CO2 doesn't increase anymore, or even starts to decrease, and what's happening in the ocean, and what is the ocean carbon sink, and especially the Southern Ocean carbon sink, doing. And then we compare the fluxes that we have today. So here you see the ocean carbon flux anomaly, or it's another word for the anthropogenic ocean carbon sink today, with large uptake again in the North Atlantic and the Southern Ocean. And now at the same time next to it, I'll show you the uptake for the time from 2100 to 2150 for the models. And this gives a very different picture. So everywhere where there's stippling, the models don't agree on the sign. And what you can see is that the subtropical tropical gyres, they still continue to take out a bit of carbon. The North Atlantic and North Pacific, they don't take up any carbon anymore, and they in some places even lose a bit of carbon. But what stands out is that the Southern Ocean really continues to be a strong carbon sink, even if atmospheric CO2 goes down. And this just shows again that this upwelling of circumpolar deep water that is hundreds of years old continues to take up so much carbon that the ocean continues to be really the only natural carbon sink once temperature stabilized, because land doesn't take up much carbon, or almost nothing. And I said the ocean, but what actually takes up the carbon is the Southern Ocean. So it's the Southern Ocean that continues to be to do a great service as a natural ocean, as a natural carbon sink. And if we didn't have the Southern Ocean, the situation would be quite different in terms of global warming and allowable emissions. So I really like how these simulations show the importance of this part of the global ocean and how we depend on the Southern Ocean and how it's unique in terms of circulation and carbon uptake. And this is basically the same plot, only integrated again over longitudes, where you see the uptake per latitude from the past to today, where there's uptake everywhere, then to the future, where when temperatures are stabilized, where the Southern Ocean continues to play the biggest role, whereas the Atlantic starts to cease fairly quickly. It's important now, but then it stops at some point. Yeah, and I would like to finish with that and say that uncertainties of Southern Ocean projections are still highly uncertain, that emergent constraints and observations can help to reduce these uncertainties, and that the disappearance of sea ice will move the Southern Ocean carbon uptake further south. And the unique circulation in the Southern Ocean really allows this region to continue to take up carbon even when global warming is halted and carbon emissions are zero and atmospheric CO2 declines. Thank you.